This is a theorem that talks about the density of rational numbers in the set of real numbers. It's because it states here that for two real numbers, we can look for a rational number in between them. This is the density theorem. It states that if x and y are real numbers with x being less than y, then there exists a rational number r element of Q such that r is greater than x but less than y. I forgot to emphasize this is actually the set of rational numbers. Okay? This would mean again that we can find, because the point here is existence. If we can just show the existence of r, a rational number in between x and y, where x is less than y, then that would mean that we have proven this theorem, because this theorem is all about the existence. So let's have here this proof. Okay, again, the point here is that in a real number line, if we have here x and this y, because x is less than y, then we can locate rational numbers here r, okay, between x and y, and that would mean that the rational numbers is dense in the set of real numbers. So that's the point here. So let's talk about this theorem. Let's have here, let x and y be element of the set of real numbers with x is less than y, because this is what is being assumed. So we're going to target the existence of r. Again, our goal is to just show r being a rational number. Okay, so with this, then if we're going to manipulate this expression, then we have, so if it's x minus y, we can just manipulate this as 0, y minus x, or we could use y minus x is greater than 0, because this has an implication for a certain corollary or connected to the Archimedean property. Okay, so by Archimedean property, there is one corollary for that which states that there exists, as long as we could structure this being greater than 0, okay, as long as we can structure that, there is a corollary which states that there exists n element of the set of natural numbers such that 1 over n is greater than 0 but less than y minus x. This is actually a corollary which states that if t is greater than 0, according to Archimedean property, then we can structure here this inequality 1 over n, and then you have here t. Okay, this is again one of the corollaries for Archimedean property, and since we have established that this is greater than 0 from this relationship, then that would be our t placing here, that would be our t here. Okay, let me change the pen color to black for more emphasis later. Then we have, by manipulating this, we only have, of course, 1 over n is less than y of minus x. It's just okay because they are all still greater than 0. And when we multiply both sides by n, you'll have 1. You'll have here n times y minus x. Or this indicates 1. Then you have here less than ny minus nx. And then if we are going to add both sides by nx, you will have nx plus 1 is less than ny. Okay, so we have this identity, or we have this expression inequality. We will be needing this. Take note, our goal later is to structure inequality where there is x and there is y. That is why we really need to go back to this. Even if there's n here, we are going to look into the perspective of it later. Now, what if we assume that our x is greater than 0? We're going to assume this so that we could use another corollary. And since a certain n is a natural number, set of natural numbers, then we can say that the product nx is still greater than 0. Nx is greater than n times 0 or just 0. Why do we again have this statement here? Because we cannot invoke another corollary for Archimedean property. Earlier, we were able to use this corollary for Archimedean property if this is greater than 0. Another here, if another thing is greater than 0, then we can invoke another corollary by Archimedean property again. There exists a certain m, let's use m because we have used already n, still a natural number such that you will have this form now. Nx, that item we used, is greater than or equal to m minus 1 but less than m. There is again another corollary which states that if y is greater than 0, earlier we used t, if y is greater than 0, according to Archimedean property, we have this inequality here. Y is greater than or equal to whatever n minus 1, if n is natural number, less than equal to n. But in this case, we used m, that's why we have this expression. Why do we do this? Okay, this is because using this side here, m minus 1 is less than or equal to nx. This implies that adding both sides by 1, m is less than or equal to nx plus 1. Why do we need this? Earlier, take note, we already have this. Let me make this asterisk. This inequality. And once this will appear, we can now combine the two. So combining them, let me have this as double asterisk. Asterisk and double asterisk. We have, again, this one here. This is asterisk. So nx plus 1 is less than or equal to m according to our double asterisk, but less than ny according to our asterisk, single asterisk. I don't have much space, so please let me copy this and add another slide. Copy. Okay, let me add another slide here. Please bear with me because this property or theorem is very important. The density theorem rather. Okay, so using this relationship we have, okay, this is what we already constructed here, combining the asterisk and the double asterisk. Okay, so by the way, I'm also copying one important inequality that we have constructed here. This one, let me copy this. Okay, because this might not be an asterisk or double asterisk, but they are very important as we construct our final statement. So let me erase the unnecessary items. Okay, this was a record in coming up with this form earlier, as we take this side only and add both sides by 1. Okay, now also remind ourselves that m and n be natural numbers. That's why we need to lock that up. Earlier we clarified them here. N is a natural number, m is also a natural number. We need to lock that as natural numbers because we are getting closer to the rational numbers, the item that we are trying to prove. Now, look into this. I would like to take this here, this portion, as we already used this portion earlier. M is greater than nx. Okay? N is greater than nx. Now, looking into this, m, this one here, this is the combination of asterisk and double asterisk. M is less than or equal to nx plus 1, but it is less than ny. So this is less than ny. Hopefully you were able to follow this. This came out from this expression, okay? While this one here is from this expression, right? So hopefully you were able to follow that. Now, after this, when we divide both sides by n, and not both sides, all sides by n, having m over n, this is greater than x, and this is less than y. Okay, take note of what we are trying to prove in our previous statement. We are trying to prove this. There is r between x and y. So there is m over n between x and y, with r be equal to m over n, which gives r as an element of a rational number. Why? Because definition of a rational number is a ratio, okay, of two other rational numbers, and since m and n are natural numbers, so the ratio of natural numbers is also a rational number. Okay? Then we can now say that r, being m over n, is greater than x but less than y, and this has satisfied our proof. Okay, so we're able to prove this, and therefore we can say that really the set of rational numbers is dense in R. Okay, so we have shown this as part of our goal. So take note of what we used here. Two corollaries of Archimedean property. This Archimedean property, okay, wherein we can have 1 over n here, and this also Archimedean property, this one here. If we have this, okay, we have n and n minus 1. Okay, they are both corollaries or Archimedean property, and of course all the necessary manipulations involving inequalities, combining all such and all the necessary details, we give R being m over n, which is a rational number, hence this as well. Okay, thank you very much for watching.